Hello there, and welcome to a gentle journey through the cosmos. I'm so glad you found your way here tonight. Maybe you've had a long day, maybe your mind is still buzzing with thoughts that won't settle, or maybe you're simply someone who finds peace in the quiet mysteries of the universe. Whatever brought you to this moment, you're exactly where you need to be. Tonight, we're going to drift through one of the most fascinating and soothing enigmas in all of science. Dark matter, that invisible silent presence that fills our universe, holding galaxies together with gentle hands we cannot see. There's something profoundly calming about dark matter. It asks nothing of us, makes no noise, creates no drama. It simply exists, quietly shaping everything we know while remaining forever hidden from view. As we explore these peaceful facts together, let your breathing slow, your thoughts soften, and your body sink into whatever comfortable space you've found. There's no urgency here, no need to memorize or analyze. Just let these gentle truths about the cosmos wash over you like whispers in the dark. And if these quiet explorations help you unwind or give you a moment of wonder before sleep, consider liking this video and perhaps subscribing for more peaceful journeys through science. It helps others find their way to these calm cosmic shores as well, one sleepy soul at a time. Now, let's begin our gentle drift into the invisible realm that surrounds us all. Dark matter makes up about 27% of everything that exists, yet we've never directly seen it. Imagine for a moment that everything you can see, every star, every planet, every grain of sand, and every human being represents only a tiny fraction of what's actually out there. All the matter we can touch and observe, what scientists call ordinary or baryonic matter, accounts for less than 5% of the universe. The rest is a quiet mystery, dominated by dark matter's invisible presence. This isn't empty space we're talking about. It's something real, something with mass and gravitational influence, threading through the cosmos like an unseen web. Dark matter doesn't interact with light, which is why we call it dark. It doesn't absorb photons, doesn't reflect them, doesn't emit them. It's as if the universe is mostly made of ghost stuff, substantial yet intangible, present yet hidden. Think of it like the wind on a still night. You can't see the air itself, but you know it's there by how it moves the leaves, how it carries sounds, how it touches your skin. Dark matter is similar, making itself known not through direct observation, but through its gentle gravitational embrace of everything we can see. The story of dark matter's discovery begins with a quiet astronomer named Vera Rubin in the 1970s. She was studying how galaxies spin, expecting to find that stars at the outer edges moved more slowly than those near the center, just like planets in our solar system. But what she found was beautifully unexpected. The outer stars were moving far too quickly. By rights all, they should have been flung out into space, their galaxies torn apart by centrifugal force. Yet there they were, held in their graceful spiral dance by something invisible, something with 5 times more mass than all the visible matter combined. Rubin's discovery was like finding that a carousel was spinning perfectly, even though you could only see a fraction of the horses. The rest were there, supporting the motion, but somehow transparent to your eyes. This revelation transformed our understanding of the cosmos. Galaxies aren't just collections of stars and gas floating in empty space. They're embedded in vast halos of dark matter, like cities nestled in invisible mountains we cannot perceive. These dark matter halos extend far beyond the visible boundaries of galaxies, creating a hidden architecture that shapes the universe's structure. Dark matter doesn't behave like the matter we know. It rarely, if ever, collides with itself or with ordinary matter. While the atoms in your body are constantly interacting, sharing electrons, forming bonds, dark matter particles slip through each other like phantoms passing in the night. Billions of dark matter particles are flowing through your body right now as you listen to this, leaving no trace of their passage. This ghostly quality makes dark matter remarkably stable. While ordinary matter clumps together to form stars that burn and die, planets that evolve and change, dark matter maintains its quiet constancy across cosmic time. It's been there since the early universe, providing the scaffolding upon which all visible structures could form. In the cosmic microwave background, that ancient light from when the universe was young, we can see the subtle imprints of dark matter's influence. Like footprints in cosmic sand, these tiny temperature variations show us where dark matter was already gathering 380,000 years after the Big Bang, creating the seeds from which galaxies would eventually grow. Computer simulations of the universe's evolution show us how dark matter might be distributed on the largest scales. These models reveal a cosmic web of dark matter filaments stretching across billions of light years, with ordinary matter following these invisible highways. At the intersections of these filaments, where dark matter is most concentrated, we find the largest galaxy clusters in the universe. The search for dark matter particles has led scientists to some of the most sensitive experiments ever devised. Deep underground laboratories, shielded from cosmic rays and other interference, house detectors waiting for the whisper-soft collision of a dark matter particle with an atomic nucleus. These experiments require extraordinary patience, sometimes running for years, to detect just a handful of potential signals. Other researchers are taking the opposite approach, trying to create dark matter particles in powerful accelerators like the Large Hadron Collider. They smash protons together at incredible energies, hoping that among the spray of exotic particles produced, they might glimpse the elusive dark matter that pervades our universe. Despite decades of searching, dark matter remains beautifully elusive. It's a humbling reminder that the universe still holds profound mysteries, that there are entire realms of existence operating just beyond our perception. In a way, this is deeply comforting. The cosmos is far stranger and more wonderful than we ever imagined. Dark matter might be made of particles with names like WIMPs, weakly interacting massive particles, or axions, theoretical particles, so light they're almost like crystallized space itself. These particles, if they exist, would have been created in the first moments after the Big Bang, relics from when the universe was unimaginably hot and dense. Some scientists propose even more exotic possibilities. Perhaps dark matter consists of primordial black holes, ancient gravitational wells formed in the early universe. Or maybe it's something we haven't even begun to imagine, a form of matter so alien to our experience that we lack the concepts to properly describe it. What we do know is that dark matter shapes the universe with remarkable gentleness. Unlike the violent explosions of supernovae or the dramatic collisions of black holes, dark matter works through gravity alone, the most peaceful of all fundamental forces. It doesn't heat up, doesn't create radiation, doesn't disrupt. It simply pulls ever so gently, guiding the cosmic dance, galaxy clusters. Those magnificent collections of hundreds or thousands of galaxies are held together primarily by dark matter's gravitational embrace. Without it, these cosmic cities would have dispersed long ago, their member galaxies scattered across the expanding universe. Instead, dark matter creates invisible baskets that cradle these galactic communities across billions of years. When galaxy clusters collide, something remarkable happens that reveals dark matter's presence. The ordinary matter, heated to millions of degrees by the collision, glows brilliantly in X-rays and gets slowed down by electromagnetic interactions. But the dark matter passes through essentially unimpeded, like two clouds of smoke interpenetrating. This separation of dark and ordinary matter during collisions provides some of our strongest evidence for dark matter's existence. The Bullet Cluster, located about 3.7 billion light-years away, shows this phenomenon beautifully. Two galaxy clusters collided about 150 million years ago, and we can see how the ordinary matter glowing in pink X-rays has been slowed and heated by the collision. But gravitational lensing reveals that most of the mass, the dark matter, has sailed through to locations far ahead of the glowing gas. This ghostly quality of dark matter creates a universe that's fundamentally more mysterious and beautiful than one made only of ordinary matter. There are entire dark matter structures out there, invisible galaxies made purely of this phantom substance, with no stars to light them up. They drift through space like cosmic icebergs, detectable only through their gravitational influence on their surroundings. Dark matter also plays a crucial role in structure formation throughout cosmic history. In the early universe, ordinary matter was too hot and energetic to clump together effectively. But dark matter, unaffected by radiation pressure, could begin gathering into the first gravitational wells. These dark matter halos then provided the foundation for ordinary matter to cool and condense, eventually forming the first stars and galaxies. Without dark matter's patient work in those early epochs, the universe might have remained a smooth, featureless expanse of cooling gas. There would be no galaxies, no stars, no planets, no life. In a very real sense, we owe our existence to this invisible scaffolding that shaped the cosmos. Long before Theon in the darkness, the distribution of dark matter in our first light-shown galaxy forms a roughly spherical halo extending far beyond. The visible Milky Way, we're sitting inside this dark matter halo right now, immersed in its invisible presence like fish swimming in an ocean they cannot perceive. The density isn't uniform, though. Computer simulations suggest it might be clumpier, with streams and substructures flowing through our galactic neighborhood. Some of these dark matter streams might be the remnants of smaller dark matter halos that have been torn apart by our galaxy's gravity over billions of years. These ghostly rivers of invisible matter flow through our solar system, carrying with them the memory of ancient cosmic encounters. As we continue our gentle exploration of dark matter's mysteries, let your mind drift with these invisible currents that surround us. There's something profoundly peaceful about knowing we're part of something so much larger, so beautifully mysterious, so quietly constant across the vast reaches of space and time. The search for dark matter has taken us to the most remote places on Earth. Deep beneath mountains in Italy, scientists have carved out laboratories in ancient rock, shielding their delicate instruments from the cosmic radiation that constantly showers our planet. In these cathedral-like chambers, surrounded by tons of stone, researchers wait in the darkness for the faintest whisper of a dark matter particle brushing against their detectors. These underground sanctuaries are some of the quietest places in the universe. The silence is so profound that even the subtle warmth of a human body can interfere with the measurements. The detectors themselves are marvels of sensitivity, capable of registering the energy equivalent of a single grain of salt dropping from a height of 1 inch. Yet despite this extraordinary precision, dark matter continues to slip through undetected, as elusive as moonbeams on water. There's something deeply meditative about this cosmic game of hide and seek. Scientists have been patiently searching for decades, refining their techniques, building ever more sensitive instruments, all in pursuit of something that may interact with our world only once in a trillion encounters. It's the ultimate exercise in scientific faith, a testament to our willingness to seek truth, even when it hides in the deepest shadows. The theoretical landscape of dark matter is equally mysterious and soothing. Physicists have proposed particles with wonderfully evocative names. Neutrinos, theoretical particles that emerge from supersymmetry, would be their own antiparticles, annihilating when they meet to produce cascades of other particles. Sterile neutrinos, ghostly cousins of the NEU we already trinos know, would interact even more weakly with ordinary matter, existing in a parallel shadow world we can barely touch. Then there are axions, named after a laundry detergent because they were supposed to clean up problems in particle physics. These hypothetical particles would be unimaginably light, trillions of times lighter than electrons, yet they could fill the universe with their invisible presence. They might even cause subtle oscillations in the fabric of space itself, creating patterns we could potentially detect with instruments sensitive enough to measure changes smaller than the width of a proton. Some of the most intriguing dark matter candidates don't behave like particles at all. Dark photons would be like ordinary light, but interacting only with dark matter, creating an invisible electromagnetic spectrum we cannot perceive. Dark atoms might form, with dark electrons orbiting dark nuclei, creating an entire periodic table of elements that exist alongside our own but never touch it directly. The possibility of dark chemistry opens up realms of speculation that feel almost like poetry. Could there be dark planets orbiting dark stars? Dark life forms evolving in dark ecosystems? These ideas stretch beyond current scientific knowledge, but they remind us that the universe might be far more richly populated than we ever imagined, teeming with forms of existence that operate just beyond our senses. Even more exotic proposals suggest that dark matter might be made of primordial black holes, tiny gravitational wells created in the first moments after the Big Bang. These ancient black holes would be smaller than atoms, but more massive than mountains, scattered throughout space like invisible seeds. They would emit no light, make no sound, but their gravitational influence would shape the cosmos with the same gentle persistence we observe in dark matter. The cosmic microwave background, that ancient light from the universe's childhood, carries subtle signatures of dark matter's influence. By studying the tiny temperature variations in this primordial glow, scientists can map how dark matter was distributed when the universe was only 380,000 years old. These measurements reveal that dark matter was already clumping together, creating the gravitational wells that would eventually become the sites of the first galaxies. The precision of these observations is breathtaking. Scientists can measure temperature differences of millionths of a degree across the sky, detecting fluctuations that occurred when the universe was 1,000th of its current age. It's like examining the wrinkles in a day-old photograph to understand events that happened 13 billion years ago. These cosmic baby pictures show us that dark matter and ordinary matter were already dancing together in the early universe, but not always in perfect synchrony. The ordinary matter was coupled to radiation, pushed around by the pressure of light itself. But dark matter felt no such pressure, free to begin the slow work of gravitational accumulation that would shape all future cosmic structure computer simulations based on these. Observations paint a picture of the universe as a vast web of dark matter filaments, stretching across billions of light years like the neural networks of some cosmic mind. At the nodes where these filaments intersect, dark matter accumulates into massive halos, and within these halos, ordinary matter can cool and condense to form the galaxies we see. The Millennium Simulation, one of the most ambitious computational projects in cosmology, tracked the evolution of billions of dark matter particles from the early universe to the present day. Running for months on supercomputers, it revealed how dark matter structures grow through gentle gravitational attraction, larger halos consuming smaller ones in a slow-motion cosmic ballet that plays out over billions of years. These simulations show that dark matter halos aren't smooth and featureless. They contain intricate substructures, streams, and clumps created by the gravitational stirring of cosmic evolution. Our own Milky Way galaxy sits within one of these complex dark matter halos, and streams of dark matter particles from disrupted smaller halos flow through our galactic neighborhood like invisible rivers. One such stream, discovered through careful analysis of stellar motions, appears to be flowing through our solar system at about 220 kilometers per second. This dark matter stream, possibly the remnant of a small galaxy that was torn apart by the Milky Way's gravity billions of years ago, represents a direct connection to cosmic history passing right through our local space. The seasonal variation in Earth's motion through this dark matter stream creates subtle changes in how dark matter particles might interact with detectors on our planet. As Earth orbits the Sun, our motion through the galactic dark matter halo changes direction and speed, creating annual modulations that some experiments claim to detect. These potential signals are incredibly faint, requiring years of careful measurement to distinguish from background noise. Dark matter's influence extends beyond individual galaxies to the largest structures in the universe. Galaxy clusters, those magnificent collections of hundreds or thousands of galaxies, are dominated by dark matter. The visible galaxies represent just the glowing tips of enormous dark matter icebergs, held together by invisible gravitational architecture. When astronomers measure the total mass of galaxy clusters by observing how their gravity bends light from more distant galaxies, they find far more mass than can be accounted for by all the visible stars and gas. This gravitational lensing effect turns galaxy clusters into natural telescopes, magnifying and distorting the images of background galaxies in ways that reveal the distribution of dark matter with exquisite precision. The most dramatic evidence comes from colliding galaxy clusters, cosmic catastrophes that unfold over hundreds of millions of years. When two massive clusters encounter each other, their ordinary matter components interact and heat up, glowing brilliantly in X-rays as gas clouds collide at speeds of thousands of kilometers per second. But the dark matter components pass through each other almost unimpeded, like two schools of transparent fish swimming through one of dark and ordinary matter during cluster another. This separation collisions provide some of the most compelling evidence that dark matter is indeed composed of particles, rather than being some modification of gravity itself. The dark matter continues moving in the direction of the original collision, while the ordinary matter is slowed and heated by electromagnetic interactions. The famous bullet cluster collision shows this phenomenon in stunning detail. The two dark matter halos have passed through each other and are now located ahead of the hot gas clouds, which have been slowed by their mutual interaction. It's as if we can see the ghosts of the original galaxy clusters continuing their journey while their more substantial remains lag behind, glowing with the heat of their encounter. As we drift deeper into these cosmic mysteries, let your thoughts become as weightless as dark matter itself, passing through the ordinary concerns of the day without friction or resistance. There's something infinitely calming about contemplating these vast, invisible presences that surround us, holding the universe together with such patient, gentle persistence across the ages. The study of dark matter has led scientists to some of the most extreme environments in the cosmos. In the hearts of galaxy clusters, where temperatures soar to millions of degrees and magnetic fields twist through space with unimaginable complexity, dark matter remains serene and undisturbed, while ordinary matter is tortured by these extreme conditions, compressed and heated until it screams in X-rays across the electromagnetic spectrum. Dark matter flows through it all like a gentle breeze through a thunderstorm. This remarkable composure in the face of cosmic violence reveals something profound about dark matter's nature. It exists in a state of perpetual calm, unruffled by the electromagnetic chaos that governs the behavior of ordinary matter. Stars may explode in supernovae that outshine entire galaxies. Black holes may devour matter in brilliant accretion disks. But dark matter observes these cosmic dramas with the detached serenity of a meditation master, watching clouds pass overhead. The gravitational lensing effects created by dark matter offer us glimpses into this invisible realm through one of nature's most elegant phenomena. When light from distant galaxies passes near massive concentrations of dark matter, space itself becomes curved, bending the light's path like a cosmic magnifying glass. These natural telescopes, formed by dark matter's gravitational embrace, allow us to peer deeper into the universe than would otherwise be possible. The images created by strong gravitational lensing are hauntingly beautiful. Distant galaxies appear as stretched arcs and multiple images, their light arriving at Earth by different paths through warped space-time. Sometimes we see perfect Einstein rings, where a background galaxy is perfectly aligned with a dark matter lens, creating luminous circles of stretched starlight. These cosmic mirages remind us that even invisible matter can create visible beauty, shaping light itself into art. Weak gravitational lensing provides an even more subtle window into dark matter's distribution. By measuring the tiny distortions in the shapes of millions of distant galaxies, astronomers can map the dark matter between us and them with extraordinary precision. It's like detecting the presence of invisible sculptures by observing how they bend the shadows they cast. Each galaxy's image carries information about all the dark matter, its light, encountered during its billion-year journey to our telescopes. These cosmic cartography projects have revealed that dark matter is distributed in a cosmic web of truly breathtaking scale and beauty. Vast filaments of dark matter stretch across hundreds of millions of light-years, connecting galaxy clusters in a network that resembles the neural pathways of a vast mind. At the intersections of these filaments, dark matter accumulates into massive nodes where the largest structures in the universe take root. Between these filaments lie cosmic voids, vast regions of space where dark matter is scarce and galaxies are few. These voids can span hundreds of millions of light-years, creating emptiness so profound that a traveler crossing one at the speed of light would see almost no galaxies for hundreds of millions of years. Yet even in these apparent deserts, dark matter maintains its gentle presence, never entirely absent, always ready to guide the formation of structure on the longest cosmic timescales. The local group, our small collection of galaxies including the Milky Way and Andromeda, sits within one of these cosmic filaments, carried along by dark matter currents that have been flowing since the early universe. We're like leaves floating on an invisible river, our motion through space guided by dark matter streams that connect us to the largest structures in existence. Within our own galaxy, dark matter creates a more intimate but equally mysterious presence. The Milky Way's dark matter halo extends far beyond the visible disk of stars, creating an invisible atmosphere that surrounds our galactic home. This halo is not uniform but filled with substructures, streams and clumps created by billions of years of gravitational evolution. Some of these dark matter subhalos may be the remnants of small galaxies that were captured and disrupted by the Milky Way's gravity in the distant past. As these satellite galaxies were torn apart, their stars were scattered into stellar streams that we can observe today, but their dark matter components created invisible streams that continue to flow through our galactic neighborhood. The Sagittarius stream, one of the most prominent stellar streams in our galaxy, marks the trail of a dwarf galaxy that has been making repeated passes through the Milky Way's outer regions. Each passage strips away more of the satellite's stars and gas, but its dark matter halo persists, creating ongoing gravitational disturbances that ripple through our galaxy's structure like waves in a cosmic pond. These tidal interactions between dark matter halos create a constantly evolving gravitational landscape within our galaxy. Dark matter clumps merge and separate, streams form and dissipate, and the overall distribution shifts subtly over millions of years. We exist within this dynamic but invisible environment, our solar system carried along by currents we cannot perceive directly. The motion of our solar system through the galaxy's dark matter halo creates opportunities for detection that change with sun, our velocity, the seasons. As Earth orbits through the dark matter wind varies, potentially creating annual modulations in the rate of dark matter interactions. Several underground experiments claim to have detected these seasonal variations, though the signals are so faint that years of careful analysis are required to distinguish them from background noise. The Dama experiment, located deep beneath the Gran Sasso mountain in Italy, has reported an annual modulation in their detector signals for more than 2 decades. This signal appears to peak in June and reach its minimum in December, exactly as would be expected if dark matter particles were streaming through the detector with Earth's orbital motion. However, other experiments have not confirmed this result, leaving the scientific community divided about its interpretation. This ongoing mystery exemplifies the patient, methodical nature of dark matter research. Scientists build ever more sensitive detectors, shield them from every possible source of interference, and then wait for years to accumulate enough data to make meaningful statements about incredibly rare interactions. It's a testament to human persistence in the face of cosmic subtlety. The theoretical zoo of dark matter candidates continues to grow more exotic and fascinating with each passing year. Asymmetric dark matter models propose that dark matter particles are left over from an ancient asymmetry between matter and antimatter, similar to the process that allowed ordinary matter to survive the early universe's annihilation epoch. These models suggest that dark matter might have its own complex history of creation and survival in the primordial cosmos. Self-interacting dark matter represents another intriguing possibility. While dark matter particles might rarely interact with ordinary matter, they could interact more frequently with each other through forces we don't yet understand. These interactions could create dark matter physics as rich and complex as the electromagnetic interactions that govern ordinary matter, potentially leading to dark atoms, dark molecules, and even dark chemistry. The possibility of dark sectors opens up realms of speculation that stretch the imagination. Could there be dark photons mediating dark electromagnetic forces? Dark electrons orbiting dark nuclei in dark atoms? The mathematics of particle physics allows for such parallel worlds of matter that share space with our own but interact only through gravity. Some theories propose that dark matter might not be perfectly stable over cosmic time. If dark matter particles decay very slowly with half-lives longer than the age of the universe, they might occasionally produce detectable signals. These decaying dark matter models could explain certain anomalous observations in cosmic ray experiments and gamma-ray telescopes. The search for these decay products has led astronomers to examine some of the darkest places in the universe. Dwarf spheroidal galaxies, small satellite galaxies of the Milky Way that contain very little ordinary matter but substantial amounts of dark matter, provide ideal laboratories for studying potential dark matter signals. These cosmic dark matter laboratories offer high concentrations of the invisible, substance with minimal backgrounds from ordinary astrophysical processes. The Fermi Gamma Ray Space Telescope has spent years scanning these dwarf galaxies, searching for the faint glow that might arise from dark matter particle annihilations. While no definitive signals have been detected, each observation places tighter constraints on the properties that dark matter particles can possess, gradually narrowing the vast parameter space of theoretical possibilities. As we continue our gentle drift through these cosmic mysteries, let your mind expand to encompass the possibility that we live in a universe far stranger and more richly populated than our senses can directly perceive. There's profound peace in accepting that vast realms of existence operate just beyond our awareness, shaping our cosmic environment with invisible hands that work only through the most gentle of all forces, gravity's patient pull across space and time. The dance between dark and ordinary matter continues across cosmic history, a slow waltz that began in the first moments after the Big Bang and will continue until the last stars fade from the sky. In this grand choreography, we are both observers and participants, made of star-forged atoms but held together by dark matter's invisible embrace, drifting through a cosmos that is far more mysterious, far more beautiful, and far more gently supportive than we ever dared imagine. The future evolution of dark matter structures unfolds like a cosmic symphony playing out across unimaginable timescales. Computer simulations that peer billions of years into the future show dark matter halos continuing their gentle merger dance, growing ever larger and more complex. These predictions paint a picture of a universe where dark matter's patient work never ceases, always building, always gathering, always providing the invisible foundation for cosmic architecture. In these distant epochs, long after the last star has formed and the universe has grown cold and dark matter will still be there, maintaining its quiet vigil. The halos will continue to evolve, driven by gravity alone, creating structures of breathtaking complexity in a cosmos that has otherwise grown still. It's a reminder that while ordinary matter burns bright and fades quickly, dark matter represents something eternal in the universe, a constant presence that transcends the fleeting drama of stellar evolution. The cosmic web itself will continue to evolve under dark matter's influence. Filaments will merge and strengthen, voids will grow larger and emptier, and the overall structure of space will become ever more pronounced. This ongoing evolution happens so slowly that entire civilizations could rise and fall without noticing the change, yet it represents one of the most fundamental processes shaping our universe. Dark matter's role in galaxy formation reveals itself through the most cosmic seeds that grew through the gradual accretion of both dark and ordinary matter. Dark matter provided the gravitational scaffolding that allowed these primordial galaxies to capture more material from their surroundings, growing slowly but steadily over cosmic time. Each galaxy we observe today represents billions of years of patient construction guided by dark matter's invisible hand. Within these ancient galaxies, the interplay between dark and ordinary matter created feedback loops of remarkable complexity. As ordinary matter fell into dark matter wells, it heated up and began to glow, eventually forming these stars. Stars then influenced their environment through radiation and stellar winds, sometimes pushing ordinary matter out of the dark matter halos that had gathered it. This cosmic conversation between visible and invisible matter continues to shape galaxy evolution today. The study of galaxy rotation curves, those measurements that first revealed dark matter's presence, continues to yield surprises. High-resolution observations of nearby galaxies show that dark matter's distribution is more complex than early models suggested. Some galaxies appear to have dense cores of dark matter, while others seem to have more diffuse distributions. These variations hint at the rich physics governing dark matter's behavior on galactic scales. Dwarf galaxies, those small cosmic islands that orbit larger systems like our Milky Way, provide particularly clean laboratories for studying dark matter. These diminutive galaxies contain relatively few stars but substantial amounts of dark matter, making them ideal for probing the invisible substance's properties. Some dwarf galaxies appear to be almost entirely dark matter, with only a sparse population of stars to mark their presence. The local group's population of dwarf galaxies creates a natural dark matter observatory in our cosmic backyard. Each of these small systems represents a different experiment in dark matter physics, with varying ratios of dark to ordinary matter and different histories of interaction with larger galaxies. By studying this diverse collection, astronomers can test theoretical predictions about dark matter behavior across a range of environments, satellite galaxies orbiting the Milky Way, and Andromeda follow patterns that reflect the underlying dark matter distribution. Their orbits carry information about the shape and extent of their host galaxies' dark matter halos, allowing astronomers to probe invisible structures through the motion of visible tracers. It's like studying the shape of an invisible pond by watching leaves float on its surface. The missing satellite problem represents one of the most intriguing puzzles in dark matter cosmology. Simulations predict that large galaxies like the Milky Way should be surrounded by thousands of small, dark matter halos, each potentially capable of hosting a dwarf galaxy. Yet we observe far fewer satellite galaxies than theory suggests should exist. This discrepancy might tell us something fundamental about dark matter's nature or about the complex physics of galaxy formation in small halos. Various solutions to the missing satellite problem have been proposed. Perhaps many dark matter halos failed to form stars, remaining as invisible satellites that surround us undetected. Or maybe dark matter interacts with itself more strongly than previously thought, preventing the formation of very small halos. Each possibility opens new avenues for understanding dark matter's role in cosmic evolution. The direct detection experiments scattered across the globe represent humanity's most patient scientific endeavor. These underground cathedrals of science operate in a realm of almost religious quiet, their sensitive instruments listening for the faintest whisper of dark matter's presence. The detectors themselves are marvels of engineering precision, capable of distinguishing between the recoil of a nucleus struck by a dark matter particle and the countless other interactions occurring in their crystalline matrices. Different detection technologies offer complementary approaches to this cosmic hide-and-seek game. Some experiments use liquid xenon, that noble gas cooled to temperatures colder than the surface of Pluto, waiting for the brief flash of light that would signal a dark matter collision. Others employ ancient crystals grown deep underground, so pure that a single dark matter interaction would ring through their atomic structure like a struck bell. The background rejection techniques used in these experiments push the boundaries of what's scientifically possible. Every material used in detector construction must be screened for radioactive contamination that could mimic dark matter signals. The experiments themselves are built using techniques borrowed from archaeological preservation, with materials, select origins, and minimal exposure for their ancient to cosmic radiation. Seasonal modulation searches represent perhaps the most elegant approach to dark matter detection. As Earth orbits the Sun, our motion through the galaxy's dark matter halo changes in both speed and direction, creating predictable variations in the rate at which dark matter particles should strike terrestrial detectors. This cosmic clock provides a unique signature that would be almost impossible to fake with conventional backgrounds. The COSINE collaboration, a joint effort between researchers in South Korea and the United States, exemplifies the international cooperation required for dark matter research. Their detectors, located in underground laboratories on opposite sides of the Pacific, compare signals simultaneously to distinguish between local backgrounds and potential dark matter interactions. It's a beautiful example of how the search for cosmic mysteries humanity brings together across cultural and geographical boundaries. Axion detection experiments pursue some of the most ethereal particles ever proposed. These hypothetical particles would be so weakly interacting that trillions could pass through your body every second without leaving any trace. Yet their sheer abundance in the universe could make them detectable through their subtle influence on electromagnetic fields. The ADMX experiment uses superconducting magnets, microwave cavities, to search for the faint radio signals that axions might produce when passing through strong magnetic fields. The search for dark photons opens yet another window into the invisible sector. These particles would be like ordinary photons, but coupled only to dark matter, creating an entire electromagnetic spectrum that exists parallel to our own, but remains forever hidden from our instruments. Dark photons might occasionally convert to ordinary photons in strong magnetic fields, creating detectable signals that would reveal this shadow world of electromagnetic phenomena. Astrophysical searches for dark matter complement the underground detection efforts by looking for the products of dark matter interactions in space. When dark matter particles occasionally annihilate or decay, they might produce gamma rays, neutrinos, or other particles that space-based telescopes could detect. These cosmic signals would carry information about dark matter interactions occurring in the most extreme environments in the universe. The galactic center region provides a natural dark matter laboratory where the high density of invisible light particles produce detectable annihilation signals. However, this region is also filled with conventional astrophysical sources rays of gamma, making it challenging to distinguish between dark matter signals and more mundane cosmic phenomena. The search requires careful modeling of all known gamma-ray sources to identify any excess that might point to dark matter. Dwarf spheroidal galaxies offer cleaner targets for indirect dark matter searches. These small, dark matter-dominated systems contain relatively few ordinary astrophysical sources, making them ideal places to search for the faint glow of dark matter annihilation. The Fermi Gamma Ray Space Telescope has spent years monitoring these cosmic dark matter laboratories, gradually improving the sensitivity of searches for this elusive signal. The cosmic ray experiments that study high-energy particles raining down from space also contribute to dark matter research. Balloon-borne detectors and space-based instruments analyze the spectrum of cosmic ray electrons and positrons, searching for signatures that might indicate dark matter or rehylation in galactic halo. These measurements probe dark matter. Interactions at energies are higher than terrestrial. Experiments can achieve neutrino. Telescopes buried deep in polar ice or anchored to the ocean floor detect the ghostly particles produced in dark matter annihilation models. When dark matter particles annihilate in the sun's core, they might produce high-energy neutrinos that could travel unimpeded through the sun's bulk to reach Earth-based detectors. These neutrino signals would provide a unique probe of dark matter. Interactions in the solar interior. The interplay between theory and observation in dark matter research creates a fascinating dialogue between what's possible and what's observed. Each null result from detection experiments constrains the properties that dark matter particles can possess, gradually excluding regions of theoretical parameter space. This process of elimination, while sometimes frustrating for researchers eager for discovery, represents genuine scientific progress toward understanding dark matter's nature. Supersymmetry, that elegant theoretical framework that doubles the number of fundamental particles, provides some of the most well-motivated dark matter candidates. The lightest supersymmetric particle would be stable and interact only weakly with ordinary matter, making it an ideal dark matter candidate. However, searches for supersymmetric particles at the Large Hadron Collider have yet to find evidence for this theoretical framework, raising questions about its role in dark matter physics. Alternative approaches to the dark matter puzzle explore whether our understanding of gravity itself might be incomplete. Modified Newtonian dynamics, or MOND, proposes that gravitational forces behave differently on Einstein galactic scales than general relativity predicts. While MOND can explain many galactic observations without invoking dark matter, it struggles to account for the behavior of galaxy clusters and the patterns observed in the cosmic microwave background. The tension between different approaches to explaining dark matter phenomena reflects the deep uncertainty that still surrounds this cosmic mystery. Some observations seem to point clearly toward particle dark matter, while others might be explained by modifications to our understanding of gravity or more exotic alternatives. This scientific uncertainty, rather than being a source of frustration, represents the exciting frontier where new discoveries await. Primordial black holes represent one of the most exotic dark matter candidates. Objects so dense that they warp space-time itself into inescapable wells. These ancient black holes would have formed in the first regions moments after the Big Bang, from where matter density happened to be exceptionally high. Unlike the black holes formed from stellar collapse, primordial black holes could have masses ranging from microscopic to stellar scales. The evaporation of primordial black holes through Hawking radiation creates potential signatures that astronomers might detect. Very small primordial black holes will apparate quickly, producing EV bursts of high-energy particles that might be visible to gamma-ray telescopes. Larger ones would evaporate more slowly, contributing to diffuse backgrounds of new cosmic rays, neutrinos, that fill the universe. Gravitational wave detectors, like LIGO and Virgo, open new windows for studying primordial black holes as dark matter candidates. When these invisible objects merge, They would produce ripples in space-time that could be detected across cosmic distances. The merger rates and mass distributions observed by gravitational wave astronomy provide constraints on how much dark matter could consist of primordial black holes. The cosmic microwave background radiation carries subtle imprints of dark matter's influence from when the universe was only 380,000 years old. These ancient photons have traveled unimpeded across billions of light years, carrying information about the density fluctuations that seeded all cosmic structure. The patterns of temperature and polarization in this ordeal, light prim, provide exquisite constraints on dark matter's properties and abundance. Precision measurements of the cosmic microwave background have determined that dark matter makes up exactly 26.8% of the universe's total energy density, with an uncertainty of less than 1%. This remarkable precision represents one of the greatest triumphs of modern cosmology, achieved by analyzing the subtle patterns in light that has traveled since the universe's childhood. The acoustic oscillations frozen into the cosmic microwave background reveal how dark matter and ordinary matter behave differently in the early universe. Ordinary matter was coupled to radiation through electromagnetic interactions, causing it to oscillate in response to radiation pressure. Dark matter felt no such pressure, allowing it to accumulate in gravitational wells, while ordinary matter oscillated around it. These different behaviors left characteristic signatures in the cosmic microwave background that we can observe today. Future observations of the cosmic microwave background promise even greater precision in measuring dark matter's properties. Space-based missions and ground-based telescopes with unprecedented sensitivity will map the primordial light with exquisite detail, potentially revealing new physics in the subtle patterns that have traveled across cosmic time. To reach our instruments, the large-scale structure of the universe provides another cosmic laboratory for studying dark matter. Galaxy surveys that map the positions of millions of cosmic islands reveal how dark matter has shaped the universe's architecture over billions of years. The clustering patterns of galaxies reflect the underlying distribution of dark matter, allowing astronomers to probe invisible structures through their gravitational influence on visible matter. Baryon acoustic oscillations, the fossilized sound waves from the early universe, appear as subtle patterns in galaxy clustering that reveal the universe's expansion history. These measurements complement cosmic microwave background observations by probing how dark energy and dark matter have influenced cosmic evolution at later times. Together, these observations paint a coherent picture of a universe dominated by invisible components. The Euclid space mission, launched to map the geometry of the dark universe, will survey billions of galaxies across cosmic time. By measuring how dark matter has shaped galaxy clustering and gravitational lensing patterns, Euclid will provide unprecedented constraints on dark matter's properties and evolution. This cosmic cartography project represents one of the most ambitious attempts to map the invisible scaffolding that holds our universe together. Ground-based surveys like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time will complement space missions by providing detailed maps of dark matter distribution across large swathes of sky. These projects will trace dark matter's influence through gravitational lensing measurements that reveal how invisible mass bends light from distant galaxies. The synergy between different observational approaches creates a powerful network for studying dark matter across all scales and epochs. From the smallest underground detectors listening for single particle interactions to the largest telescopes mapping cosmic structure across billions of light years, humanity has assembled an impressive arsenal for probing the universe's invisible majority. As we drift deeper into contemplation of these cosmic mysteries, there's something profoundly calming about dark matter's patient persistence. It has been there since the universe's youth, quietly shaping every structure we see, from the smallest dwarf galaxies to the largest cosmic filaments. Its presence is so fundamental that without it, the universe would be a vastly different place. perhaps one incapable of supporting the complexity that gave rise to stars, planets, and ultimately consciousness itself. In the gentle darkness that surrounds us, dark matter continues its ancient work, holding galaxies together, guiding the flow of cosmic evolution, and maintaining the invisible architecture upon which all visible beauty depends. It asks nothing of us, creates no disturbance, makes no demands. It simply exists as constant and reliable as the passage of time itself, a cosmic companion that has journeyed with us across the ages and will continue long after our brief moment in cosmic history has passed. There's deep peace in knowing that we are held within this invisible embrace, that the universe's structure rests on foundations more stable and enduring than anything we can see or touch. As your thoughts begin to drift like dark matter particles through the quiet spaces of sleep, let yourself be carried by these gentle cosmic currents that have flowed since time began and will flow long after time ends, in the beautiful darkness that binds everything together. The search for dark matter has led humanity to some of the most creative experimental approaches ever devised. Scientists have proposed using quantum sensors so delicate they could detect the gravitational influence of a single dark matter particle passing nearby. These devices would operate at temperatures a fraction of a degree above absolute zero, in chambers more isolated from vibration than spacecraft, floating in the void between stars. Researchers explore the possibility that dark matter might occasionally interact with the quantum fields that permeate space itself. If dark matter particles can couple to the Higgs field that gives other particles their mass, they might create tiny ripples in this fundamental fabric of reality. Detecting such interactions would require instruments sensitive enough to measure changes in the vacuum of space, smaller than the wavelength of light itself. The concept of dark matter hurricanes has captured the imagination of both scientists and the public. These theoretical structures would form when our solar system occasionally passes through dense streams of dark matter flowing through the galaxy. During such events, the local density of invisible particles might increase dramatically, potentially making them easier to detect with terrestrial experiments. Computer models suggest that these dark matter storms could last for thousands of years, creating extended periods when detection experiments might be more likely to record signals. Some researchers speculate that we might currently be experiencing such an event, which could explain certain anomalous readings in underground detectors that have puzzled scientists for years. The possibility of dark matter weather patterns within our galaxy adds another layer of complexity to the detection challenge. Just as Earth's atmosphere contains high and low pressure systems that create changing weather, the galaxy's dark matter halo might contain streams, eddies, and currents that vary over time. These invisible atmospheric patterns could create temporal variations in dark matter density that future experiments might learn to predict and exploit. Dark matter archaeology represents another frontier in the search for invisible particles. Some theoretical models suggest that dark matter interactions might leave trace signatures in ancient materials on Earth. Researchers have begun analyzing billion-year-old mineral samples, searching for microscopic, damaged tracks that could have been created by dark matter, particles colliding with atomic nuclei in the distant past. These geological dark matter detectors would have been operating for far longer than any human-built instrument, potentially accumulating signals over cosmic timescales. The challenge lies in distinguishing ancient dark matter interactions from the countless other processes that can create similar damage patterns in rocks and minerals over geological time. Meteorites provide another natural dark matter laboratory, having spent millions of years in space where they might have accumulated interactions with passing invisible particles. Some researchers analyze the crystal structures in these space rocks, searching for defects that could reveal the subtle fingerprints of dark matter. Encounters during their long journey through the galaxy, the study of ancient ice cores offers yet another approach to dark matter archaeology. Ice sheets in Antarctica and Greenland contain layers of frozen atmosphere spanning hundreds of thousands of years. If dark matter particles occasionally decay or annihilate, they might have produced distinctive isotopes that became trapped in these frozen archives of Earth's atmospheric history. These paleoclimate records of potential dark matter interactions would complement modern detection efforts by providing information about how dark matter density and properties might have varied over geological timescales. Changes in the galactic environment, such as our solar system's passage through different regions of the Milky Way's halo, could create signatures detectable in these natural records. The biological effects of dark matter represent one of the most speculative but intriguing aspects of invisible particle research. If dark matter occasionally interacts with ordinary matter in living organisms, it might influence biological processes in subtle ways. Some researchers have proposed that dark matter interactions could contribute to genetic mutations, potentially playing a role in evolution itself. These ideas remain highly speculative, but they highlight the pervasive nature of dark matter's potential influence. Every atom in every living organism on Earth exists within the galaxy's dark matter halo, constantly bathed in streams of invisible particles. If even the tiniest fraction of these particles interact with biological matter, the cumulative effect over evolutionary timescales could be significant. The search for dark matter biosignatures would require careful analysis of mutation rates, DNA damage patterns, and other biological processes that might be influenced by rare particle interactions. While extraordinarily challenging to detect against the background of known mutagenic processes, such research could reveal entirely new connections between cosmic phenomena and terrestrial life. Dark matter's role in planetary formation adds another dimension to its cosmic influence. As the early solar system condensed from a rotating disk of gas and dust, dark matter particles would have been present throughout the process. Some models suggest that dark matter accumulation could have influenced where and how planets formed, potentially affecting the architecture of planetary systems throughout the galaxy. The gravitational influence of dark matter clumps within protoplanetary disks might create density waves that guide the formation of asteroid belts, influence planetary migration patterns, or affect the delivery of water and organic compounds to forming worlds. These subtle influences could help explain why some planetary systems develop Earth-like worlds while others remain barren. Exoplanet surveys that discover thousands of worlds orbiting other stars provide natural laboratories for testing dark matter's influence on planetary formation. The statistical properties of these distant planetary systems, their orbital architectures and compositions, might carry signatures of dark matter's role in cosmic construction processes. Some researchers propose that dark matter could even affect the long-term stability of planetary orbits. While these effects would be incredibly subtle, accumulating over millions or billions of years, they might influence the habitability of worlds by gradually changing their distance from their parent stars or altering the tilt of their rotational axes. The possibility of dark matter planets represents one of the most exotic extensions of invisible particle physics. If dark matter can interact with itself through forces analogous to electromagnetism, it might be capable of forming complex structures including dark atoms, dark molecules, and even dark matter worlds, orbiting dark matter stars in a parallel universe that shares space with our own. These shadow worlds would be completely invisible to our telescopes, detectable only through their gravitational influence on ordinary matter. They could exist right alongside visible planets, creating binary systems where one world is made of familiar matter while its companion consists entirely of exotic particles we cannot perceive directly. The atmospheric sciences of such dark worlds would operate according to entirely different physics, with dark matter particles playing the roles that atoms and molecules play in familiar atmospheres. Dark weather patterns might sweep across these invisible surfaces, driven by dark radiation from dark stars in complex cycles. that mirror the meteorology of ordinary worlds. Dark matter life, if it exists, would face entirely different evolutionary pressures and opportunities than biological organisms made of ordinary matter. Dark ecosystems might develop their own forms of chemistry, metabolism, and information storage, creating biospheres that exist in parallel with our own but remain forever beyond the reach of conventional observation. The philosophical implications of such possibilities stretch the imagination toward questions about the nature of existence itself. If consciousness can arise from the complex interactions of ordinary matter, might similar processes occur within dark matter structures? Could there be dark civilizations pondering their own invisible universe while remaining unaware of the bright world of stars and galaxies that shares their space? These speculations venture far beyond current scientific knowledge, but they illustrate the profound mysteries that dark matter research continues to unveil. Each new observation, each refined theoretical model, each more sensitive detector brings us closer to understanding the invisible majority of our universe while simultaneously revealing how much we still have yet to discover. The technological spillovers from dark matter research have revolutionized fields far beyond particle physics. The ultra-sensitive detectors developed for finding invisible particles have found applications in medical imaging, environmental monitoring, and industrial quality control. The computational techniques used to simulate dark matter structure formation now help meteorologists predict weather patterns and engineers design more efficient transportation networks. The international collaborations required for dark matter research have created new models for scientific cooperation that transcend national boundaries and cultural differences. When faced with cosmic mysteries of such magnitude, human divisions seem as insubstantial as the dark matter particles themselves, bringing researchers together in pursuit of understanding that belongs to all humanity underground. Laboratories originally excavated for dark matter experiments now host a diverse array of scientific investigations, from neutrino astronomy to studies of the deep biosphere. These facilities represent some of the quietest places on Earth, sanctuaries where scientists can probe the fundamental nature of reality without interference. From the electromagnetic chaos of surface civilization, the patient methodology required for dark matter research has influenced how we approach other long-term scientific challenges. Climate studies, biodiversity conservation, and space exploration all benefit from the disciplined, persistent approach that dark matter researchers have refined over decades of searching for the barely detectable educational programs inspired by dark matter. Research introduces young minds to the wonder of invisible realities that surround us. Students learn that the universe is far stranger and more mysterious than it appears, fostering the kind of open-minded curiosity that drives scientific discovery. Dark matter serves as a perfect metaphor for the hidden depths that lie beneath surface appearances in every field of knowledge. The cultural impact of dark matter extends beyond science into art, literature, and philosophy. Writers and artists find inspiration in the concept of invisible influences that shape visible reality, while philosophers grapple with questions about the nature of existence and perception that dark matter research has brought to the forefront of human consciousness. Public. A deep human need to understand our place in the fascination with dark matter reflects cosmos. The idea that we are immersed in an ocean of invisible matter connects with ancient intuitions about hidden realities, while the scientific precision of modern dark matter research satisfies our desire for evidence-based understanding of these mysteries as detection technologies continue to improve and theoretical understanding deepens. The next decade promises to be particularly exciting for dark matter research. New underground facilities with unprecedented sensitivity are coming online. Space-based telescopes with revolutionary capabilities are being planned, and theoretical physicists continue to develop increasingly sophisticated models of how dark matter might behave. The convergence of multiple detection strategies creates the possibility that dark matter's identity might finally be revealed through the simultaneous observation of complementary signals. A particle detected in an underground laboratory, annihilation products observed by space telescopes, and gravitational signatures mapped by cosmic surveys could together provide the definitive evidence that has eluded researchers for so long. Yet even if dark matter's fundamental nature remains hidden, the search itself continues to enrich our understanding of the universe in profound ways. Each negative result teaches us something new about the properties that dark matter cannot possess. Each technological advance opens new windows into cosmic phenomena we never knew existed. The story of dark matter research embodies the best qualities of human scientific endeavor: patience, precision, creativity, and the willingness to spend decades pursuing answers to questions that may not be resolved within a single generation. It represents our species' deepest commitment to understanding reality, even when that reality remains stubbornly invisible. In the gentle darkness of space, dark matter continues its ancient dance, shaping galaxies, guiding cosmic evolution, and maintaining the invisible architecture that makes our existence possible. It surrounds us with the constancy of an old friend, present in every cubic centimeter of space, flowing through our bodies and our world with the persistence of time itself. As your awareness drifts toward the peaceful realm of sleep, let yourself be carried by the thought of these invisible currents that connect us to the deepest structures of the cosmos. Dark matter asks nothing of us except wonder, offers nothing except its quiet presence, and promises nothing except that the universe will always be more mysterious and more beautiful than we can fully comprehend. In this cosmic darkness that holds all light, in this invisible substance that makes all structure possible, we find not emptiness, but fullness, not absence, but the most fundamental presence of all. The darkness that cradles galaxies cradles you as well, and in that embrace, there is perfect peace, perfect mystery, and perfect rest. The dance between theory and observation in dark matter science reveals itself through the most delicate measurements ever attempted. Scientists have learned to distinguish between signals so faint they register only a few interactions per year from backgrounds so subtle they require underground facilities shielded by entire mountains. This patient methodology has created a new form of scientific listening, where researchers tune their instruments to frequencies of existence that operate just beyond the threshold of human perception. Some of the most promising detection approaches involve quantum interferometry, where scientists create devices so sensitive they can measure distortions in space-time itself caused by passing dark matter particles. These instruments operate by splitting laser beams and recombining them after they've traveled through regions where dark matter interactions might occur. Any subtle change in the path length, even changes smaller than 1,000th the width of a proton, could reveal the presence of invisible matter flowing through our local space. The cryogenic systems required for these experiments create some of the coldest environments in the known universe, colder than the depths of interstellar space. In these frigid conditions, thermal noise drops to levels where individual dark matter interactions might finally become distinguishable from the background chaos of ordinary matter. The refrigeration systems themselves are marvels of engineering, capable of maintaining temperatures within thousandths of a degree above absolute zero for months at a time. Magnetic field configurations in these experiments reach intensities that would be impossible to achieve on Earth's surface, where cosmic radiation and electromagnetic interference would overwhelm hope to detect. Deep underground, shun the delicate signals researchers shielded by billions of tons of rock, scientists can create magnetic environments pure enough to reveal the subtle signatures of dark matter's passage. The timing systems used in dark matter detection require precision that rivals atomic clocks, capable of measuring intervals shorter than the time light takes to cross a single atom. These temporal measurements allow researchers to correlate signals across multiple detectors, distinguishing between genuine dark matter interactions and random coincidences that might mimic the signatures they seek. Collaborative networks spanning continents coordinate these measurements, creating effective detectors larger than entire countries. When a potential signal appears in one underground laboratory, researchers can immediately check whether corresponding signals appeared in facilities thousands of miles away. This global coordination represents one of the most sophisticated, real-time scientific monitoring systems ever created. The statistical analysis required to extract dark matter signals from experimental data pushes the boundaries of mathematical sophistication. Researchers must account for seasonal variations, lunar cycles, geological instabilities, and countless other factors that could influence their measurements. The resulting data analysis pipelines process information with computational power that would have been unimaginable when dark matter was first discovered. Machine learning algorithms trained on millions of simulated dark matter interactions help scientists recognize patterns that might indicate genuine particle collisions. These artificial intelligence systems can identify subtle correlations in detector responses that human researchers might overlook, effectively extending our perceptual capabilities into realms of data complexity that exceed natural cognitive limits. These materials, science innovations driven by dark matter research, have created substances purer than anything found naturally on Earth. Crystal growth techniques developed for detector construction produce materials with fewer impurities than the best laboratory diamonds, while surface preparation methods achieve cleanliness levels that approach the theoretical limits of atomic perfection. Underground facilities themselves represent remarkable feats of construction, with excavations that extend deeper into Earth's crust than most natural caves while maintaining environmental stability that rivals the most controlled laboratory conditions. These subterranean cathedrals of science create spaces where the boundary between natural and artificial environments dissolves into something approaching the cosmic quiet that pervades deep space. The psychological aspects of dark matter research require a unique form of scientific patience. Researchers must maintain enthusiasm and precision while working on timescales that extend far beyond individual careers. Many scientists dedicate their entire professional lives to experiments that may not yield definitive results until decades after their initial conception. This extended temporal perspective creates research cultures that transcend normal academic rhythms, where progress is measured not in publications per year, but in incremental improvements in sensitivity that accumulate over generations. The institutional memory required to maintain such long-term projects represents a form of scientific continuity rarely seen in other fields. Training. Programs for dark matter researchers emphasize not just technical skills, but also the mental discipline required for persistent investigation of phenomena that may interact with our instruments only a few times per century. Graduate students learn to find satisfaction in null results, understanding that each non-detection provides valuable constraints on theoretical possibilities. The engineering challenges posed by dark matter detection have spawned entirely new subdisciplines within physics and materials science. Techniques for achieving ultra-high vacuum conditions, for minimizing radioactive backgrounds, and for maintaining mechanical stability over extended periods have applications far beyond particle physics research. Seismic isolation systems developed for dark matter. Detectors can distinguish between genuine particle interactions and vibrations caused by earthquakes occurring on the opposite side of the planet. These systems create islands of mechanical stillness so profound that they approach the theoretical limits imposed by quantum mechanical uncertainty. B. Electronic systems used to process signals from dark matter detectors operate at noise levels that challenge fundamental physical limits. Amplifiers cooled to temperatures approaching absolute zero achieve sensitivities where individual electron movements become significant sources of interference. requiring circuit designs that account for quantum mechanical effects in everyday electronic components, data storage and analysis systems. For dark matter, experiments generate and process information at rates that rival major internet companies, yet must maintain precision and reliability standards that exceed those required for most scientific applications. The resulting computational infrastructure represents some of the most sophisticated real-time data processing systems ever created for fundamental research international. Cooperation in dark matter research has created new models for scientific collaboration that transcend traditional academic and national boundaries. Shared detector technologies, coordinated observation schedules, and joint analysis protocols have established frameworks for cooperation that could serve as templates for addressing other global scientific challenges. The economic impacts of dark matter research extend far beyond the direct costs of experiments and facilities. Technological innovations developed for particle detection find applications in medical imaging, environmental monitoring, industrial quality control, and national security applications, creating economic returns that often exceed the initial research investments. Educational outreach programs associated with dark matter research introduce students to concepts that bridge the gap between abstract theoretical physics and tangible experimental investigation. These programs demonstrate how the most esoteric scientific questions can lead to practical technological developments that benefit society in unexpected ways. The philosophical implications of dark matter research continue to evolve as our understanding deepens. Questions about the nature of reality, the limits of human knowledge, and the relationship between observation and existence take on new dimensions when applied to substances that may forever remain beyond direct perception. Cultural representations of dark matter in literature, film, and art reflect humanity's fascination with invisible influences that shape visible reality. These creative interpretations, while often scientifically inaccurate, serve important functions in helping people process the conceptual challenges posed by a universe dominated by imperceptible matter. But religious and spiritual communities have found various ways to incorporate dark matter concepts into their understanding of existence, seeing parallels between invisible cosmic influences and traditional teachings about unseen spiritual realities. These interpretations, while distinct from scientific understanding, demonstrate the universal human need to find meaning in cosmic mysteries. The next generation of dark matter experiments promises to push detection sensitivities to levels where background noise from ordinary astrophysical processes begins to interfere with the search for exotic particles. This approaching threshold represents both a challenge and an opportunity, as it may force researchers to develop entirely new experimental approaches. Proposed space-based dark matter detectors would escape the terrestrial backgrounds that limit ground-based experiments, potentially achieving sensitivities impossible to reach on Earth's surface. These orbital laboratories would operate in the pristine environment of deep space, where cosmic ray backgrounds are predictable and electromagnetic interference is minimal. The possibility of using the Moon as a platform for dark matter detection offers intriguing advantages, including geological stability that exceeds anything available on Earth and isolation from terrestrial radio frequency interference. Lunar-based experiments could operate for decades without the maintenance requirements that limit the duration of Earth-based investigations. Theoretical advances continue to expand the range of possible dark matter candidates, with new models proposing particles and interactions that would require fundamentally different detection strategies. Some theories suggest that dark matter might exist in multiple varieties, creating a hidden periodic table of invisible elements with their own complex chemistry and physics. The potential discovery of dark matter would rank among the most significant scientific achievements in human history, comparable to the discoveries of DNA, quantum mechanics, or general relativity. Such a breakthrough would not only solve one of cosmology's greatest mysteries, but would also open entirely new fields of physics and astronomy for exploration. Yet even if dark matter remains elusive, the search itself continues to drive technological innovation and scientific understanding in directions that benefit humanity in countless unexpected ways. The patient pursuit of cosmic mysteries represents one of our species' most noble endeavors, demonstrating our willingness to invest in knowledge that may not yield practical benefits for generations. In the quiet depths of underground laboratories around the world, sensitive instruments continue their vigil, listening for whispers from the invisible realm that surrounds us. These mechanical sentinels represent humanity's most sophisticated attempt to extend our senses into realms of existence that natural evolution never prepared us to perceive. The steady hum of cooling systems, the soft glow of monitoring displays, and the patient presence of researchers maintaining their watch create an atmosphere of technological meditation. In these spaces, the boundary between science and contemplation dissolves into something approaching reverence for the profound mysteries that govern our cosmic home. As detection sensitivities approach theoretical limits and computational power continues to expand, the next decade may finally yield the breakthrough that reveals dark matter's true nature. Or perhaps the mystery will deepen, leading us toward even stranger possibilities that current theories cannot imagine. Either outcome would represent a triumph of human curiosity and persistence. The willingness to spend decades searching for phenomena that interact with our world only through gravity's gentle pull demonstrates a form of scientific faith that transcends immediate practical concerns, reaching toward understanding for its own sake. In the cosmic darkness that fills the spaces between stars, dark matter continues its ancient journey, carrying the memory of the universe's birth and the seeds of its future evolution. It flows through galaxies and planets, through laboratories and living beings, connecting all things in an invisible web of gravitational influence that operates with the constancy of natural law. This hidden realm that surrounds us offers a profound lesson in humility, reminding us that reality extends far beyond the narrow band of existence accessible to our biological senses. The universe is not only stranger than we imagine, but perhaps stranger than we can imagine, filled with layers of reality that operate according to principles we are only beginning to glimpse. As your thoughts drift towards sleep, carried by the gentle currents of consciousness that mirror the flow of dark matter through space, let yourself be comforted by the knowledge that you exist within something far grander and more mysterious than everyday experience suggests. The invisible ocean that bathes our galaxy also bathes you, connecting your brief existence to the deepest structures of cosmic reality. In this darkness that holds all light, in this silence that underlies all sound, in this invisible presence that makes all visible structure possible, there is perfect peace. The same forces that guide galaxies through their stately dance also guide you toward rest, cradling you in the gentle embrace of cosmic mystery that has endured since time began and will continue long after human memory fades into the patient darkness of deep space. This cosmic web of dark matter filaments creates pathways through which galaxies migrate over billions of years, like cosmic highways guiding the slow dance of stellar cities across the expanding universe. These invisible thoroughfares carry information about the universe's earliest moments, preserving the patterns that emerged when space itself was younger than light could travel across what would one day become our solar system. Within these vast networks, dark matter flows in currents that predate the formation of the first stars. Streams of invisible substance that began their journey when the cosmos was still hot and dense with primordial energy. These ancient rivers continue to flow today, carrying galaxies along predetermined paths that were established in the universe's infancy before atoms existed, before light could travel freely through space. The gravitational choreography orchestrated by dark matter operates on timescales that dwarf human comprehension. While civilizations rise and fall in cosmic instants, dark matter structures evolve with adapting the universe's architecture through processes epochs, gradually scull the patience of geological so gentle they're barely perceptible even across millions of years. Some theoretical models suggest that dark matter might undergo phase transitions, similar to how water becomes ice or steam, but occurring under conditions of density and temperature that exist only in the most extreme cosmic environments. These transitions could create regions where dark matter behaves differently, forming crystalline structures or liquid-like flows that remain forever hidden from our instruments. The possibility of dark matter. Superfluids introduces concepts borrowed from the most exotic states of ordinary matter. In these hypothetical conditions, dark matter might flow without friction or resistance, creating currents that persist for cosmic ages without decay. Such superfluid dark matter could explain certain anomalies in galactic rotation patterns that even standard dark matter models struggle to address. Deep within the cores of galaxy clusters, where gravitational forces reach intensities that warp space itself, dark matter may exist in states that have no analog in terrestrial physics. The extreme conditions in these cosmic pressure cookers could compress dark matter into forms so dense that they approach the threshold where quantum effects become significant, even on astronomical scales. And now, as we reach the end of our gentle journey through the invisible cosmos, let your thoughts settle like cosmic dust in the quiet spaces between stars. We've drifted together through the hidden architecture of the universe, from the patient work of dark matter in shaping the first galaxies to its continuing dance in the depths of space that surrounds us even now. In this invisible ocean that cradles all existence, there is profound peace. Dark matter asks nothing, disturbs nothing, yet holds everything together with gravity's gentle embrace. As you rest tonight, remember that you are part of this cosmic story, woven into the very fabric of space and time by forces more ancient and enduring than light itself. Sleep well, knowing that the same mysterious presence that guides galaxies through their eternal waltz also watches over your dreams, in the beautiful darkness that binds all things together.